Welcome to lecture number 5 for ECE476, Advanced Embedded Systems. In this lecture, we're looking at binary outputs. So to give an idea of where we're heading, this is an Raspberry Pi Pico breakout board from Adafruit. Same as the one we're using, just has LEDs attached to all the I/O pins and doesn't have a graphic display, but still a pretty nice board for 10 bucks. Here I've got a pin turning on and off that's driving an LED. We'll look at how to do that in this lecture. That LED is then driving a DC motor, turning it on and off. We'll look at how to do that as well. We'll also look at how to turn the Raspberry Pi into a parallel output, so I can write to all the pins, and in this case create something like the Knight Rider, old TV show where the LEDs bounce back and forth. How we do that in Python. And finally, we'll look at how to send Morse code. So for example, this is sending out NDSU in Morse code to a flashing light on GP13. Tie that to a buzzer, and it'll be going dee 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 dee, and so on, giving Morse code. So that's where we're heading. Okay, so starting out, the Raspberry Pi Pico has 25 I/O pins. Those are the general purpose input-output pins, and each pin can be binary input or binary output. They also have other functions. These aren't grouped into ports like they were with the Raspberry Pi or with the PIC microcontroller. For example, this is again the breakout board from Adafruit. Again, you don't need this for this class. I'm just using it because I don't feel like wiring up all these LEDs, and it shows off better for the lecture. These are called GP0, GP1, GP2, and so on. So each of these are basically standalone pins. There aren't ports. With the microchip processors, along with many other processors, there's a port. When you write to port A, I'm writing to 8 bits. The Raspberry Pi doesn't have ports. And that's kind of good and bad. The logic levels on the ports. Anything below 0.8 volts is read as logic level 0. Anything between 2 and 3.3 volts is logic level 1. Again, this is a 3.3 volt device. You don't apply 5 volts to the device. The data sheets do have a safety margin. The Raspberry Pi Pico can tolerate voltages up to 3.6, but 5 volts is way out of specs, so you shouldn't be applying 5 volts to Raspberry Pi Pico. No guarantee what's going to happen. What we're looking at in this lecture is driving an LED, driving a buzzer, making it beep 5 times, or output Morse code. How to get more power out. Again, the Raspberry Pi Pico can only do 12 milliamps. Suppose I want more power. I can do that by buffering it with a BJT transistor or an H-bridge. I can do parallel output. I can write to all the different pins, treating it like an 8-bit or 16-bit port. I can drive multiple outputs, have a display routine so I can see what's happening, and I can do some timing. So I can do things like I have a counter and Morse code. So that's what we're getting to today. Let's start out with making a light blink. So on your PIC board, there are 2 LEDs. One's attached to pin GP16, one's attached to GP17. Or on the Adafruit board that I'm using, they're all tied to LEDs, but here's 16 right here. How do you make that light blink? Well, one way to do that is the following code. I'm going to import subroutine pin from library machine. Machine kind of has the hardware subroutines in it. Import the subroutine sleep from time. Then I'll set pin 16 to output, and then go into a for loop. For 10 counts, I'm going to toggle pin 16, toggle LED, sleep point 1 second, and repeat. After 10 times, turn off the LED. So that's kind of how the program works. Again, these guys we'll talk about a little bit. These are the libraries that let you control the inputs and outputs. I have to tell you what the pin is, input or output. In this case, it's output, input's next lecture. How many times I want to toggle it, toggle the pin, then sleep. And what that looks like, can I change that to 100 just for demo? Change that to 10 and run that puppy. You see the light blinks. After 10 blinks, it turns off. I changed it to 1 second. Suppose I want to use the beeper. Switching boards to the GeeekPi board, I can make it beep 5 times. Again. Okay, the way that works is the beeper is tied to GP13. If I apply 5 volts to GP13, correction, if I turn on GP13, 3.3 volts, it beeps, 0 volts, turns off. So here all I do is, again, I import the subroutine pin from machine, import sleep from time. I'll use the pin subroutine. I'm going to declare GP13 is output and assign it the name beeper. Then for 10 times, I'm going to toggle beeper, sleep point 1 second. After 10 toggles, turn it off. So again, here's what that looks like or sounds like. Take this off to make it louder. So a little bit of background on what's happening. I'm using some of the standardized modules, machine and time. Modules are standardized subroutines that either you wrote or other people wrote. Once you get your subroutine pretty much solidified, so you're not going to change it anymore, you can throw it into a library that you can access over and over again. This is similar to what you did in C. In C, I could access different modules using an include statement. I would say #include the standard io.h or include math.h. That would be C code. In Python, I use the command import and the name of the module, like import machine, import time, import math. Now to access the subroutines inside the module is a little bit different than C. In Python, you include the name of the module along with the name of the subroutine. What's nice about that is it avoids conflicts. Like suppose math had a subroutine called sleep and time had a subroutine called sleep. With this format, it tells the compiler which subroutine do I want. I want the sleep subroutine for module time. That way there's no conflict. And likewise to access it, if I want to do cosine function, this is the subroutine cosine from math, the constant pi from math, and the subroutine sleep from time. Now that can get a little bit cumbersome, so there's a shortcut. If I say from math import sine cosine pi, from time import sleep, if I do that, that only brings in these subroutines. That saves some memory. But also, to address it, I don't have to say math.cosine, math.pi, time.sleep. I can just say cosine, pi, and sleep. However, if you do that, you got to make sure there's no conflicts. So if two different subroutines, two different modules have subroutines with the same name, I got a problem. So that's kind of a shortcoming of this approach, but it does make the code a lot easier to understand. If you want to know what's inside a module, I can do help. So for example, if I go over here and Python, give me some more room. Come on, puppy dog, where are you? There you are. Get the syntax right. Say help modules. That'll tell you all the different modules that are available. And we're not going to be using all of these, but if you do a search online, web's great. You can find out all sorts of stuff on the internet. If you want to know about a specific module, like what's inside the routine machine, these are all the different subroutines within the module machine. And we're not going to cover all of them, just kind of a useful subset. If you see something that you like and want to know more about it, I can say directory of machine, and it tells the name of the different subroutines within that module. If I want to know more about a certain function, I can say help machine.pin. And Python is case sensitive, so these are all the different options for the subroutine pin. So with that, let's turn on and off an LED. So let's make pins 16 and 17 turn on and off. On the Arduino, or on the Raspberry Pi Pico, the logic levels are 0 volts and 3.3 volts. 0 volts is logic level 0, 3.3 volts is logic level 1. Each pin is capable of sourcing or syncing up to 12 milliamps. If I want to make those pins output, I'll do pin 16 or 17, comma, pin.out. That makes them output. To make them input, we'll do pin.in, but that's our next lecture. Actually, that won't compile because I have to do machine.pin. If I use this syntax, I have to say from machine import pin. To turn on and off an LED, I've got a couple options. If I do toggle, that toggles it, 1 goes to 0, 0 goes to 1. If I do value of 1, that sets the pin. Value of 0 clears the pin. High turns it on, sets it. Low turns it off. And I can also print, if I want to see on the screen, what's the value of that LED. So to illustrate that, I can go down to here, from machine, import pin, and do like LED equals pin. Let's make it pin 16, pin.out. So it's the LED over here in the corner. I can now say LED.toggle. And you might see that LED turning on and off. Or let's go to the upper left corner. Let's make that pin 0. Just saw that LED turn off. If I toggle it again, it just turned off. I can do LED.value of 1 is now set. Value of 0 is cleared. If I just do LED.value, that actually is a read command. It says, what is the value of pin 0? It's currently off. If I set it and read it, it's now 1. And the time library, there's a command called sleep. What sleep does is it locks up the processor for that many seconds. And there's a couple versions. There's sleep, which 1.234 will wait 1.234 seconds. Sleep milliseconds waits that many milliseconds. Microseconds sleeps that many microseconds. For example, if I make pin 16 output and toggle it 20 times, here's what it looks like. See that light blinking 20 times. Or if I run this code, it's going to turn on the light for 1 second, turn it off for 1 second, then toggle 10 times. And running that, so I'm going to change it to LED 0, that one right there, so you can see it. It turns on for 1 second, turns off 1 second, then blinks or toggles 10 times. With the Raspberry Pi Pico, it uses slightly different syntax than the Arduino. If you're familiar with the Arduino uses commands like GPIO, pin, and value. So I could say like GPIO 0, 1, turn on bit number 0. I can mimic that with the Raspberry Pi Pico. I would define your output pins, like this is pin 16 through 26, is LED 0, LED 1, LED 2. I'll set each pin to output. Then here's my GPIO subroutine. If I want to say turn on bit 0, then it's going to say if it's a 1 or a 0, I'm going to either set 1 or clear. If I do something like -1 or 2, it toggles. And that's the value. The pin is which one you're looking at. So 0 would be pin 16, 1 would be pin 17. With that syntax, I can say turn on GPIO 0, which is 16, turn off GPIO 2, 17, toggle GPIO 4, 0, 1, 2, 3, 4, 20. So you could use Arduino syntax if you want. We're not going to do that for the rest of the semester. So that's basically inputs and outputs, 1s and 0s. If I want to drive a load, like an LED, it depends upon how much current that load needs. If the load needs less than 3.3 volts, less than 12 milliamps, I can drive it directly. Just use a resistor to limit the current. For example, suppose I want to drive this red LED. The voltage drop across the LED is 2 volts. The VI characteristics of a diode look kind of like this. So it's 2 volts when turned on. The color is a non-scientific term. The wavelength is more accurate, more precise way of defining color. The millicandles at 20 milliamps, that's how bright it is, and the cost. If I want to drive this at 10 milliamps, well, at 20 milliamps, it's rated at 2.0 volts. Because this is exponential, at 10 milliamps, it's still basically 2 volts. That's an ideal diode model. So if I want 10 milliamps flowing through it, if I've got a 3.3 volt output from the Raspberry Pi Pico, I lose 2 volts across the LED. The resistor, so here's your 3.3, 2 volts across the LED. The resistor sees the difference, 1.3 volts. 1.3 volts at 10 milliamps is 130 ohms. So buffer the diode to the Pico with the 130 ohm resistor. That'll set the current to 10 milliamps. That's kind of what's done on most of the boards. If I need more than 3.3 volts or more than 12 milliamps, I need a transistor as a switch. So suppose I want to do something like this. Let's drive a 3-watt LED from the Pico board. The 3-watt LED needs 3.6 volts and it needs 750 milliamps. Both are a problem. The Pico cannot output 3.6 volts. It cannot drive 750 milliamps. So we need a buffer circuit. Well, one of the buffers that works pretty well is just an NPN transistor. So I'm going to go the Pico over here, use a transistor as a switch. A transistor is a current-controlled current amplifier. This guy, the 6411 NPN transistor, has a current gain of at least 300 or 200. So 1 milliamp from the Pico will produce 200 milliamps at the transistor. Then I can have my LED, my power supply. If this is supposed to be 750 milliamps, more than the PIC can drive, the PIC has to supply that divided by 750. So the PIC has to drive at least 3.75 milliamps. To design the circuit, this is RC. Here's RB. First, find RC. If I have a 5 volt power supply, that 5 volts, I want to find the voltage across the resistor. That 5 volts loses 3.6 volts across the LED. That comes from the data sheet. Loses 0.36 volts across the transistor. That leaves the remainder across the resistor. I want 750 milliamps, so from voltage over resistance, or voltage over current gives me resistance, I want a 1.3 ohm resistor at the collector. That sets the current. To find RB, I want this to be at least 3.75 milliamps, but no more than 12 because the Pico can't drive more than 12 milliamps. Pick a number between 3.75 and 12. I chose 10. If you choose 10 milliamps, then I've got 3.3 volts over here, 0.7 volts across the transistor, because this is a diode. Volts drop across the silicon diode is 0.7. The remaining voltage at 10 milliamps gives you the resistance 260 ohms. So there's the circuit that turns on and off an LED. And cut a note that this is actually pretty generic. As far as the transistor is concerned, it will turn on and off any load as long as the current here, IB times beta, which is 200. 200 times IB is more than IC. 200 times 10 is 2000, 2 amps. This will drive any load that needs less than 2 amps. To illustrate that, here I've got my transistor. The output comes from GP0, goes into the base resistor. The transistor acts as a switch. I've got my 5 volts, goes to the motor, to the collector. Collector goes to the emitter through the transistor. Emitter goes to ground. And what you get is when the Pico outputs 3.3 volts, when GP0 turns on, the motor turns on. Now this motor can draw up to 2 amps with this circuit. The Pico only outputs 10 milliamps. So with 10 milliamps, I'm turning on and off a motor at up to 2 amps. That's the beauty of a BJT transistor, acts as a buffer. Note on inductive loads. Let's turn that off. If you have an inductive load, this is basically storing energy. The energy is stored as 1/2 Li squared. So when it's turned on, there's current flow. When I turn off the transistor, where's the energy go? What happens is if I turn off the transistor, the energy has to go somewhere. The magnetic field collapses, forcing the voltage to go to infinity. As VC goes to infinity, it will find a path to ground. It will find a way to discharge that inductor. If I take out this diode, the path to ground is through the transistor, and you just fry the transistor. To save the transistor, I need a flyback diode. What that does is this is a limiting function. Normally, there's no current flow through the diode's in backwards. If this tries to go above 12.7 volts, the diode turns on and saves the transistor. So this clips it at 12.7 volts. That's the flyback diode. If you ever connect a motor, it works fine for a couple seconds, then dies. Try another transistor, plug it in, works a couple seconds, then dies. What's killing it is the inductance. You need a flyback diode to provide the current with a path to discharge the coil when you turn off the current. Okay, that's what it just said. So that's a transistor to switch. Now, one problem with the transistor, current only flows one way. So I can have the motor flow forward. Let's turn that on again. So here I can turn the motor on and off. How do I make the current go backwards? This circuit can't do that. To make the current go backwards, I need a different circuit. For forward and reverse directions, use an H-bridge. So what an H-bridge does is if this is your motor, say right here, your load, if I turn on T1 and T4, current flows left to right, that'd be forward. If I turn on transistors 3 and 2, current goes this way, that's reverse. So with a single 12-volt supply, or any supply, I can make the motor go forward and backwards just by turning on and off the different transistors. That's an H-bridge. So with an H-bridge, you actually have 4 modes of operation. I've got forward, current goes this way. There's a slight drop across each transistor, usually about 0.2 volts is what we assume. So it's the 12 minus 0.2 twice. I get plus 11.6 volts across the motor going forward. If I turn on T3 and T2, I get minus 11.6 volts. And kind of notice, relative to the motor, I'm getting plus and minus voltage, even though I only have a single power supply. Third mode of operation is everybody turns off. That means the motor's just spinning freely, coasting. Fourth mode of operation, turn on T2 and T4. I short the leads. What happens is the motor acts as a generator. It produces current. Current gets burnt up as I squared R heat in the armature resistance. I'm converting kinetic energy into heat. That's active braking. The fifth mode is turn everybody on. That just shorts power to ground. You're not supposed to do that. So technically there are 5 different modes. 4 of them are useful. The fifth one is destroy the H-bridge. So that's an H-bridge. In electronics, we build those. In this class, we can just buy one. For $1.98, you can buy an H-bridge from Amazon. So here I've got an H-bridge connected to the motor. So here's my little H-bridge. Pins 16 and 17 go to these 2 pins. That controls the H-bridge output. 5 volts in ground going to the H-bridge. When I want to go forward, I'll turn on 16, turn off 17. To stop, I turn everybody off. To go reverse, I do the opposite. Turn off 16, turn on 17. So here's what she looks like. You can see this. It goes clockwise, counterclockwise, forward, reverse. A little bit easier to see on a voltmeter. So it's going to go reverse, minus 3.28 volts. This voltage across the motor. 0, plus 3.29, 0. So here I'm applying plus minus voltage using a single 5-volt supply. I'm actually losing about 1.6 volts across the H-bridge. Those are the transistor losses. But the important thing is I'm getting both positive and negative voltage with a single power supply. That's an H-bridge. So the connections, I've actually got 2 H-bridges on your device. I'm using the one on the right. Here's where the motor goes. This goes to your Pi Pico board. There's the second H-bridge on the left-hand side. This is the 5 volts to the H-bridge. The power supply to the motor, anything between 5 and 35 volts. I'm just using 5 volts because I have it available. In terms of software, as I apply 0, 0, I get 0 volts out, 0, 1, plus voltage, 1, 0, negative voltage, 1, 1, 0 voltage. So what's happening over here, you can see it with the LEDs. Kind of get this wire out of the way. So these are the 2 LEDs driving it. There's the 1, 0, 0, 1, and the voltage that you're seeing on 0, 1, plus 3 volts, 1, 0, minus 3 volts. So H-bridges, again, are just pretty darn useful. Disconnect it, save the power. If you just need something to turn on and off, I can use the BJT transistor. If I want to have it change direction, go forward, reverse, I can use an H-bridge. The inputs, again, are just binary inputs, stuff that the Pico board does really, really well. Note, however, that I'm only getting 0%, 100% speed. It's either full power forward, full power reverse, or nothing in the middle. You can do partial on and off. That'll be using pulse width modulation, something coming up a little bit later. All right, so let's look at some parallel output. I've got different LEDs attached to the Pico board. Each one is standalone, separate. Can I write to 8 bits at the same time, treat it like a port? Well, of course, the answer is yes. I can do almost anything in software. I write a subroutine to make it look like a port. So here's where we're heading. I want to treat a bunch of pins like these as an 8-bit port. So I write to it, here I'm just counting. I want that count to show up on these LEDs. And this is kind of why I'm using the Adafruit Pico board. It's got the LEDs attached to the I/O pins, so I don't have to wire them. And you can see the binary output a lot easier. How do I do that? Well, on the Pico, all the I/O pins are separate, kind of standalone pins. There aren't really ports. That's good. If I want to create a port, I can make the pins anything I want. That's bad because it makes it kind of hard to write to 8 bits at a time. However, with software, I can mimic an 8-bit port. So just for fun, I'm going to make pins, these pins right here, look like an 8-bit port. Again, the good thing is I can have any pins I want. I now have an 8-bit port. That's all good. The bad thing is when I write to this port, it's not going to write to all 8 bits at the same time. There's actually a slight time skew between the first bit and the last bit. In terms of coding, here's what the code looks like. I'm going to define which pins are port A. So here I said pins 16 through 26 are port A. I'm going to make each of those pins output, come up with a subroutine called display, and that just shows me what is the value of each pin on the console. Here's the subroutine that I want. Binary out. If I write the number 55, I want the bins to run 0101, that's 50101, 55 hex. To do that, I'm going to check each bit one at a time. If the least significant bit is a 1, that's X and 1, I'll then set that bit of port A, otherwise clear it. Do the second bit, third bit, fourth bit, go for the entire length of A, however many bits are in that port. And to illustrate that, I'm just going to count. Let's just count and display it. So here's what it looks like. Here's the actual code. I changed it so it's pins 15 through 8. That's the pins on the left-hand side. And as I run it, you count to 1,000. You can see that pins 15 through 8 are counting. There's the most significant bit. What's kind of nice about that, let's stop this puppy, stop that puppy. I can change the pins around. Let's go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's make this an 11-bit port. Make it count a little bit faster. An 11-bit port starting from pin 0. So if I run that code, you can see that it's counting. Here's the least significant bit, most significant bit. I now have a 11-bit counter. Now that's one of the nice things about this. I can put the pins anywhere I want. I can assign any order I want. I can make it as many pins as I want. Some of the nice things about the way Raspberry Pi handles the I/O pins. Another example, I can have a light blink a fixed number of times. Tell it I want to blink 5 times, and it should see the light blinking 5 times. Trying that, let's see. Find the right program. Run that boy, and I'm going to blink light 0 up here. Tell it to blink 4 times. Blink, 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 blink. You might be able to see it right here. There's the light blinking. Blink 3 times. Blink, blink, blink. 2 times or 1 time. Blink. 55 times. Blink, 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 blink. Again, kind of say that only engineers get excited by a light blinking. That means a lot. That means your code downloaded, it compiled, it's accepting your keyboard input. Kind of a big deal. Next thing to do for fun. Let's create the Night Writer program. So here's what I want. On the left are the LED bouncing up and down. How do I do that? Well, we're almost there. I'm going to define a port to be GP0 through GP15, have the binary output, write a number to it. I'll have the number just be power 2. So here's 1, 2, 4, 8, 16. Based upon the number, it would be which light is turned on. Take that number, shift it right to go down, shift it left to go up. That's times 2, divide by 2. What the code looks like is this. I define the port. Now the port is 16 bits. Initialize to output. Write to each bit. Start with the most significant bit turned on. Shift left. When I get to the right side, shift right. Keep going until I get to the left side. And here's what it looks like. There's 1, 80, 1, 8000, 1, 8000. And the net result is you have a blinking light. Again, the board that I'm using is, this is actually a $10 board from Adafruit. It's got LEDs attached to the I/O pins, which is kind of nice for this lecture. You can use it on any board. I'm just using it for this lecture, about the last time I'll be using this board. But for this one, when I want to see the binary outputs, it's kind of nice. Finally, let's output a Morse code signal. Let's do NDSU and Morse code. So in this case, I'm going back to the board that we're using in this class. I've got the little buzzer beeping out NDSU in Morse code. S, U, N, D, S, U. How do you do that? That's my volume control. So to do that, I'll do bottom-up programming. First, let's do the dits and dash. A dit is 100 milliseconds on, 100 milliseconds off. A da is 300 milliseconds on, 100 milliseconds off. The standard in Morse code is 3 to 1. A pause between letters is a 300 millisecond pause. An N is a da dit pause. D is da dit dit pause. S is dit 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 pause. U dit dit da pause. Next level up. Do NDSU repeat. I've got Morse code. Let's stop that. Oops. Gotta stop it while the buzzer's turned off. Okay, so in summary, with a Pi Pico, you can turn on and off devices using general purpose I/O pins. If you need a load less than 3.3 volts and less than 12 milliamps, the Pi Pico can drive it directly. You just need a resistor to limit the current. If you need more voltage or more current, you can connect it to a device like a BJT transistor for one direction, or an H-bridge if you want to have bidirectional output. And with software, I can also cluster GPIO pins together to create ports. These allow you to drive multiple devices with a single Pi Pico board. So you can do that, but that's actually not what's intended. They really intend you to use serial output, but that's a future lecture. So that's lecture number 5 for ECE476. Our next lecture will look at binary inputs.